In the midst of World War II, the world faced an enemy that seemed unstoppable: Germany. The chance of a German invasion was looming. Germany's army, air force, and navy sent thousands of encrypted messages every day containing crucial orders and strategies. These messages were completely indecipherable, entirely due to a German machine called the Enigma. The Enigma machine was integral in providing the Axis powers with the upper hand during World War II, specifically during the Battle of the Atlantic. At this time, Britain was heavily reliant on supplies from the United States and Canada to sustain its population and war efforts. However, German submarines created blockades, intercepted shipments, and endangered lives. The Enigma machine allowed Germany to securely transmit classified information, ensuring that their operations remained hidden from the Allied forces. Decoding these messages from the Enigma was considered an impossible task, and each day that the code remained unbroken, vital supplies were delayed and lost, and countless lives were placed at risk. Well, enter Alan Turing, a brilliant mathematician and a cryptographer. In 1939, as the war escalated, Turing took on a full-time role at Bletchley Park in Buckinghamshire. His primary mission? To break the seemingly impenetrable Enigma code. So this is a story of how math, logic, and one man's vision cracked the uncrackable Enigma and helped bring down World War II Germany. Alan Turing was a man of brilliance, a mathematician, logician, cryptanalyst, and the pioneer of computer science. In fact, when you read his Wikipedia page, you're going to think, really, Alan, what didn't you do? I mean, my Wikipedia page will probably be a sentence. Born in June 1912, Turing grew up in southern England, where his natural talent for mathematics and problem-solving quickly became apparent. Turing's groundbreaking work laid the foundation of modern computing. He developed the concept of the Turing machine, a theoretical model that defined the foundation and principles of algorithms and computing. In fact, this work actually earned him the title of father of theoretical computer science, as it introduced ideas that continue to shape technology we use today. By 1938, Alan Turing completed his doctorate at Princeton University. But it was during the World War II that Turing's genius really, truly changed the course of history. At the outbreak of the war, Turing joined the Government Code and Cipher School at Bletchley Park, Britain's secretive code-breaking hub. Here, Turing led Hut 8, the team responsible for breaking the German Navy's encrypted communication. And this was no small task. This was a significant turning point in the war. The German military really relied on the Enigma machine, a device that they considered was unbreakable. And it was Alan Turing and his team that helped the Allies break Enigma. And this was a significant turning point in the war. But what exactly is the Enigma, and why is it such a feared device? The Enigma machine was invented by German engineer Arthur Scherbius in the early 1920s. Initially, it wasn't designed for military use. It was intended for commercial purposes, and it was marketed to businesses that needed to send confidential messages. This does sound like it was marketed to shady companies, but I mean, Enigma was previously marketed to banks and even governments to protect sensitive communication. Yes, banks and governments could be shady, but that's a whole new topic. Anyway, as tensions in Europe grew in the 1930s, Germany's military saw the potential of using a machine to encrypt messages during the war. The German military began modifying the initial design to make it more secure and started using it extensively during the late 1920s. By the time World War II began in 1939, the German Army, Air Force, and Navy were using advanced versions of the Enigma machine to encrypt all of their communications. And like I said, Germany considered the Enigma machine unbreakable and used it to coordinate nearly every top-secret operation in the military. This confidence gave the German forces significant advantage in the early years of World War II. And this was more than evident during the Battle of the Atlantic. The Atlantic was Britain's lifeline. Britain is an island nation, of course, despite it not having island weather. But at the time, Britain heavily relied on imports of food, weapons, fuel, and raw materials from allies like the United States and Canada. These supplies arrived via convoys of merchant ships crossing the Atlantic, and Germany had its sights set on cutting off these supply lines. The German Navy, with its formidable fleet of submarines called U-boats, launched a relentless campaign to blockade Britain. They hunted down and sank merchant ships, attempting to choke Britain's war effort and starve its population into submission. The German Navy used the Enigma machine to actually coordinate their U-boat attacks. It allowed them to send encrypted orders to submarines patrolling the Atlantic. These messages revealed things like convoy routes, ship locations, strategic instructions, ensuring that German forces could outmaneuver the Allied ships. The Allies could intercept these messages, but the messages were encoded. Without the ability to decode them, the messages were useless. They just didn't make sense. And without knowing the exact positions of the U-boats, Britain couldn't really effectively defend its convoys or even plan counterattacks. So breaking the Enigma code became a matter of survival for Britain. The British government knew that cracking the Enigma code could turn the tide of the war. So they knew Enigma was important, but they also knew that breaking Enigma was even more important. And in order to break the Enigma, they needed to know how it worked. This is the Enigma, and yes, it looks like an oversized typewriter. And its primary purpose was to encrypt and decrypt messages. Operators would type letters of their plain text messages into the keyboard, and the machine would output a new scrambled letter that replaced the original letter. At the receiving end, the process was reversed. The encrypted message, or ciphertext, would be typed into the Enigma machine, and it would output the original message, as long as both machines were configured to the exact same settings. This is how it worked. The story starts at the plug board, a panel in front of the Enigma machine. The plug board is like a switchboard, where pairs of letters could be swapped before they enter the machine. For example, if the plug board is set to swap A to M, then pressing A will send the signal for M into the machine instead. Not all letters are swapped though, only ones that are connected via the cables. This creates a layer of scrambling that makes the encryption even harder to crack. Once a letter passes through the plug board, it's ready for the next step. Next, the signal moves into the rotors, the most famous part of the Enigma machine. These are 3 or more rotating disks which are each wired internally in a scrambled pattern. When the signal enters the first rotor, it's redirected into a new letter. For instance, M from the plug board may turn into X. But it doesn't stop there, because the signal then travels to the second rotor, where it's scrambled again, and in the third rotor, where it's scrambled for a final time. So each rotor adds an additional layer of complexity, turning the input into something seemingly random. What makes a rotor even more fascinating is how they move. After each key press, the first rotor moves one position, changing the pattern on how letters are scrambled. Then, when the first rotor completes a full rotation, the second rotor advances by one position. Eventually, the third rotor also moves too. And this constant rotation ensures that the encryption is always changing, even if you type the same letter twice in a row. So, for example, pressing A once might produce the letter X, but pressing it again might produce the letter G. After passing through the rotors, the signal reaches the reflector at the back of the machine. The reflector is like a mirror. It sends the signal back through the rotors, retracing its path but scrambling it even further. This means that the signal travels through the rotors twice, once on the way to the reflector and once on the way back. And because of this, the reflector has an interesting feature which later on turns into a flaw. It ensures that no letter can ever be encrypted as itself. For example, A could never be encrypted into A again. While this feature added a complexity to the Enigma's design, it also introduced an imperfection that the Allied codebreakers would use. Once it's reflected, the signal returns to the plug board for one final transformation. And this final step completes the encryption process. The machine then reveals the encrypted letter. A small light bulb lights up and displays the output. For example, after all the scrambling, your original A might now appear to be a Z or a Z. The encrypted letter is recorded, and then the process starts again for a new letter. And what made the Enigma so powerful wasn't just the complexity of its internal mechanisms. It was the fact that these mechanisms could be reconfigured every day. Each morning, operators of the Enigma received a codebook that specified the starting positions of the rotors, the order of the rotors, and the different plugboard connections. With these daily settings, the Enigma actually produced a completely different encryption pattern each day. So even if enemies intercepted a message, they couldn't decode it at all without knowing that day's specific configuration. And that made it harder to crack. By the time Alan Turing arrived at Bletchley Park, the challenge of breaking the Enigma code had only grown to be more daunting. Deciphering messages from the Enigma became really critical in protecting the convoys and rerouting ships to avoid the German submarines during the Battle of the Atlantic. So now, more than ever, the Enigma needed to be cracked. But the story of cracking the Enigma didn't begin at Bletchley Park. Before the war, a group of Polish cryptanalysts, Marian Rajkowski and his team, had made a critical breakthrough. The Polish team had received stolen Enigma blueprints, and they had reverse-engineered early versions of the machine. They identified patterns in how the encryption worked and exploited flaws in the system, successfully decoding messages. But in 1939, as the war loomed, Germany also upgraded the Enigma and introduced new layers of complexity, layers that rendered the Polish methods ineffective. So realizing that they couldn't keep up with the changes, the Poles shared their findings with Britain, and their work became the foundation for what Turing and his team would later achieve. But Alan Turing and his team was left with a complex Enigma machine that they needed to break. Turing approached the problem with fresh ideas, focusing on logic and automation. And one of the things he realized was that these messages were sent by the German military. Surely these messages have some common phrases, like there was a weather report, and usually there are specific phrases when you speak about the weather, or the fact that Germans often included the infamous greeting in a lot of the communication. I don't think I can say the greeting without being flagged, but we all know what that specific greeting is. It's the salute that praises their dictator at the time. So the Turing team figured out that the operators had routines and specific phrases that they would use. For example, weather reports were quite constant in military communication, and often it was beginning with the word Wetter, which is German for weather. Quite similar, German operators were known to use standard phrases like this. I'm not trying to pronounce that, but that meant nothing to report in German. And these common repeated elements became the key to unlocking the Enigma. The team called these predictable phrases cribs. And then by aligning a suspected piece of plain text, i.e. the crib, to its encrypted counterparts, they could narrow down the possible settings of the Enigma for that day. So for example, if they suspected wetter would appear in the messages, they would match it to different parts of the intercepted ciphertext and then look for logical matches. For example, if they suspected that wetter appeared in the messages, they would then look at the intercepted ciphertext and match it to the different parts, essentially looking for logical matches. The strategy was revolutionary, but it wasn't enough on its own. The sheer number of possibilities still required too much manual testing. That's when Turing and his team designed the Bombe, a machine that would do the heavy lifting. And it was this machine that finally cracked the Enigma. The Bombe was an electromechanical device that was designed by Alan Turing and his team at Bletchley Park. Its purpose was to figure out daily rotor settings of the Enigma machine, an essential step to decrypt the German messages. Each day, German operators changed the Enigma machine settings, resulting in 150 trillion possible combinations. The Bombe's role was to reduce this number to a few likely connections, which then could be manually tested fairly quickly. This is how it was done. The code-breaking process began by identifying a crib, which was a piece of plain text that likely appeared in the encrypted message. For example, weather reports often started with the word wetter, which meant German for weather. So let's say the crib was attack at dawn, and it's matched to a specific part of the ciphertext or the encrypted text. So the ciphertext is this, and the crib or the plain text that matches is this. And this alignment gave the Bombe a starting point to analyze potential rotor settings. Once the crib and the ciphertext or encrypted text were aligned, the cryptanalyst created a menu. This was a logical diagram which showed the connections between the letters of the crib and the ciphertext. The menu represented how each letter might have been encoded through the Enigma machine. So, for example, plain text letter A might correspond to ciphertext letter W. At another position, A might correspond to P, and so on. This relationship was graphed into a network, which you can see here, with loops and links representing the different connections. So looking at this image, from crib to cipher, A at the 4th position of the plain text translates to P in the encrypted text. And then A at the 7th position translates to K belonging to the encrypted text. Then you get K at the 6th position of the plain text translates to the letter L. And then it was also mapped backwards. So from the encrypted text to the plain text, which you can see here. L is at the 8th position of the encrypted text, and that translates to T in the plain text. And then T at the 10th position of the encrypted text translates back to A in the plain text. And eventually this menu would have loops indicating various patterns. The number of loops or cycles in the menu actually determined how efficiently the bombe could process the problem. More loops reduced the number of false stops during testing. Once a menu was completed, the bombe was configured based on the menu. The bombe used rotating drums that replicated the wire and behavior of the Enigma rotors. Each drum simulated one rotor, and the bombe was set to test thousands of possible initial rotor positions based on the patterns from the menu. The actual menu connections between the letters were physically wired into the bombe. Once that was done, testing started. The bombe began running, simulating the Enigma machine's encryption processes for the different rotor settings, depending on what the Germans had decided. So here's how it worked. Let's say it tested the crib, i.e. attack at dawn, against the ciphertext, which is this. Here it looked for logical contradictions. For instance, if the crib suggested that A should encrypt to W, but the same settings caused W to encrypt back to B, the rotor configuration was eliminated because it didn't match the menu. However, if you type A and it encrypted to W, and then typing W encrypted back to A, that was good. The symmetry ensured that the encryption and decryption processes were identical as long as the machine settings were the same. Because remember, in the Enigma, you had one operator sitting somewhere typing in the plain text, you had another operator receiving the encoded text and then needed to decrypt it. So ideally, the encryption and the decryption should be the same. This also introduced a rule. No letter could ever encrypt itself. For example, A could never encrypt to A, W could never encrypt to W, and so on. And this no self-encryption rule was actually a weakness of the Enigma because it was just an extra pattern that they knew the Enigma would not do. So the bombe would test the different possibilities and eliminate the ones that didn't fit the menu and didn't make sense. And the process of eliminating these contradictions dramatically narrowed down the possibilities of the settings for the Enigma. And once the bombe found a configuration that didn't result in any contradictions, it stopped. These were called stops and actually represented your potential Enigma settings. Cryptanalysts could then manually test these settings on a replica Enigma. So they would input the settings and then try to decrypt the encoded message. If the output matched the plain text, they had successfully found the Enigma's daily configuration and could use that to decrypt all of the German messages coming through that day. Using similar logic, I created a Python script to replicate the Enigma machine as well as the bombe decryption. So the Enigma encrypts messages by scrambling letters through a combination of rotors, which you can see here. There's also a reflector and a plug board, as well as the rotors rotating after each letter to ensure that constantly changing encryption. And using these known initial settings that can be changed, the script encrypts a plaintext message into a ciphertext. In my example, my plaintext message was, "Enemy is coming," and I type that in and run the script. The script will then output the encoded or ciphertext, which is this. To decode this message, the script now simulates how the bomb would solve the encryption. So what the bomb does is that it simulates the Enigma machine and tests all possible router configurations while searching for that one crib, which I've selected as enemy. And once the bomb identifies the matching settings, it then reveals the full message that's decoded. This is obviously just a very simplified version of what is happening. And I'm sure there's a few things wrong with my script, but it just shows the pure genius of the Enigma and the bomb. The bomb wasn't just a machine. At its heart, it was an incredible feat of engineering and logic that could do what humans simply couldn't do: process possibilities at lightning speed. Imagine sitting at a desk, manually testing trillions of Enigma configuration, hoping that one works. It would take years just to crack a single message. And the bomb changed all of that. And while the bomb didn't win the war on its own, it was a crucial tool that gave the Allies an edge in the fight. It was a symbol of how intelligence, logic, and relentless determination could overcome even the most complex of challenges. Alan Turing and his team really took on a challenge that seemed impossible. They combined mathematical genius, engineering innovation, and determination to turn the tide of World War II. Thank you so much. If you like my content, please like, comment, and subscribe. I'll see you on the next one. Cheers.